In this video, we will talk about electric potential. We will first use work kinetic energy theorem to introduce electric potential energy. We will then see how the concept of electric potential naturally follows from the concept of electric potential energy. We will then extend these discussions to point charge systems, and we will be doing a few examples in the process. Let's look at a following system. What do you have here? You have a positive point charge, and it is moving in a region with electric field heading rightward. So since the electric field is, let's say, along the x-axis, we know the electric force that is acting on this charge Q will also be going in that direction, with a magnitude given by Q times E. Let's assume that this charge travels between 2 points. The initial point with x-coordinate xi and the final point with an x-coordinate of x sub f. And of course, the motion is purely under the influence of this electric force due to that electric field. Since there is a force acting on this object that causes the object, in this case the charge Q, to be displaced by that much distance, we should be able to compute the work done by this force. From our earlier video on work, we know the expression for the work done by a constant force such as that in displacing an object that by that much distance is given by the following expression: force times displacement. So in this case, the force is Q times the electric field, and the displacement is xf minus xi, the final x-coordinate minus the initial x-coordinate. We also know from work kinetic energy theorem that the work done on this charge must be the same as the change in kinetic energy of that charge. The change in the kinetic energy of the charge is the final kinetic energy minus its initial kinetic energy, namely the kinetic energy the charge had at this point, subtract the kinetic energy the charge had at that point. Now, since we are dealing with a conservative force here, the change in the kinetic energy must be negative the change in the charge's potential energy. Thus, equating this expression to that expression, we get the following: QE delta x, with delta x equals to that, equals minus delta U, where delta U is the change in the potential energy of the charge. As is the case with any form of energy, the potential energy is measured in the unit of joules, and since it is a form of energy, it is a scalar. The next thing that we want to introduce is the electric potential, the product of the electric field times the displacement equals minus the change in electric potential. So what that means is it's minus the potential, the electric potential at the final point, namely there, subtract the electric potential at the initial point, which is there, and that is quite simply VI minus VF. Now we note that V is a scalar, the electric potential is a scalar, and it is measured in an SI unit of volt. So we see that the change in electric potential and the change in electric potential energy are indeed related, and they are given by Q delta V equals delta U. Let's write down this expression in full. So Q V final minus V initial equals U final minus U initial. Now that means the electric potential energy is quite simply the electric charge times the electric potential the charge is moving through. When an object moves in a field, its potential energy will naturally decrease. So when this charge moves from this point to that point, what happens to the potential energy, the electric potential energy? It goes down. Or we say the change in electric potential energy of that charge is negative. But since the change in electric potential energy is related to the change in electric potential in that manner, where delta V is the electric potential at the final point subtract the electric potential at the initial point, delta V must also be negative. That means your initial point electric potential must be greater than the electric potential of the final point. What this all means is that if a charge were to move between 2 points, these 2 points must have different potentials, with initial point's potential must be greater than the final point's potential. For example, in this case, if the initial point is at 100 volts and the final point is at a potential of 50 volts, then this positive charge would go naturally in that direction. Let's do a quick example to illustrate the point. A proton is released from rest at x equals to -2 cm in an electric field whose strength is 1000 Newton per Coulomb in the direction of positive I hat. Calculate the change in the potential energy of the proton when it gets to x equals to 5 cm. So the change in the electric potential energy of a charge is given by -q e delta x. So q is the charge of the proton. So the charge of proton is 1.602 times 10 to the power minus 19. The electric field strength is 1000, so times 1000. And this is the displacement of the charge. The displacement of the charge is that 5 minus 2. So that's 7 centimeters. Convert that into meter by dividing that by 100. And you will get the following answer for the change in its electric potential energy. Minus 1.12 times 10 to the power minus 17 joules. Next, we want to apply all the things that we have covered so far to a point charge system. Now let's assume the electric field is indeed created by a point charge with a strength capital Q. So this charge capital Q creates an electric field in an outward direction as shown here. Now let's assume there is a test charge, a plus test charge, little q, initially at a distance r from that capital Q. Now this point charge obviously will move to the right. Let's say in doing so, it moves from the initial point I to the final point F. Let's assume the coordinate of the initial point is Ri, the coordinate of the final point is Rf. We want to determine the electric potential energy for such a system, for such a point charge system. As we said before, the work done on this charge by that charge, because this field is created by this capital Q. So the work done on this little q is minus the change in the electric potential energy of the system, which is the initial electric potential energy minus the final electric potential energy of the system. But we do know work is given by an integral of force dr. Because the force is the electric force dotted into the displacement of this charge as it moves from this point to that point. The electric force is given by Q times the electric field produced by this charge when the object is moving, when the little q is moving, and that electric field is given by K capital Q over R dr from Ri to Rf. Do not forget the square because the electric field comes with R squared. Note, I'm using the following result. Force is given by QE and electric field is given by KQ, because it's the capital Q that's creating the electric field at the location of little q, KQ, over the distance between them squared in a radial direction, or the radial direction is taken to be in that direction. And dr, this vector right here, can be written as radial unit vector times dr. So this dotted into this is 1, and you get that result. One could solve this integral quite easily, and you're going to get minus k little q capital Q over r, substituting the upper and the lower limit, which will result in this. Now comparing this expression to that expression, we can immediately write down an expression for the electric potential energy of the system, and that is quite simply given by K, the product of the two charges over the separation between them. Note, this expression is the electric potential energy of the system consists of two charges. Now it's relatively straightforward to determine the electric potential, let's say at some point R. Electric potential is 1 over Q times the electric potential energy. So 1 over Q, Q is the test charge, KQ capital Q over R, and you get KQ over R. So this is the electric potential in the unit of volts produced by this charge at some distance r from it. Note the difference in the expression for V and U. U contains the product of two charges, whereas V contains only the charge that's producing that potential. Let's look at the following example. You have a 3-point charge system, and you want to determine the electric potential energy of the system consisting of 3-point charges instead of 2, as we discussed earlier. So if you have more than 2 charges, all you have to do is to consider them in pairs. So Q1 and Q2 first, Q1 and Q3 first, and then Q2 and Q3 first. So let's do Q1 and Q2 combination. We're computing the potential energy, so it's K, the product of the two charges is 1.602, they are electrons. So the charge of an electron is that, do not forget to square, divide by the distance, which in this case is 2 times 10 to the power minus 10 meter. Now let's do 1 and 3, so you have to sum 1 and 3 combination to the 1 and 2 combination. So that is the expression for 1 and 3 potential energy. The distance between them is 4 times 10 to the power minus 10 meter. And the final term that you need to add is 2-3 term. And the 2-3 term is given by that. And the total electric potential energy of the system is given by 2.88 times 10 to the power minus 18 joules. Note that this K is 9 times 10 to the power 9. It's a constant that appeared in Coulomb's law. Next example, we have Q1 is a positive charge with a strength 5 microcoulomb at the origin, and Q2 is a negative charge with a strength 2 microcoulomb at x equals to 3. Now we want to determine the electric potential these two charges create at that point P at y equals to 4. So the potential at P consists of the potential due to Q1 at P plus the potential produced by Q2 at point P. The potential due to Q1 is quite simply K. Q1 is 5 times 10 to the power minus 6. It's 5 microcoulomb. It's positive. And the distance between them, R, is a 4. The potential produced by this charge will be negative because it's a negative charge, K. The charge is 2 times 10 to the power minus 6, and the distance between Q2 and the point of observation is 5 by Pythagoras' theorem. This is 3, this is 4, so this has to be 5. So R is 5 for that. And when you solve it, remembering K is 9 times 10 to the power 9, you will get 7,650 volts for Vp, namely potential at this point due to these two charges. Thanks for watching.